In the darkest days of the Cold War, the Pentagon asked a question that bordered on insanity. What if we built a nuclear missile that never had to land? They didn't just want a weapon that could kill. They wanted a predator. They wanted a machine that could launch, fly across the ocean, and then wait. A nuclear vulture that could circle the globe for days, weeks, even months, waiting for the order to dive. To build it, American engineers had to invent a new kind of engine, an engine that breathed air but burned uranium. An unshielded nuclear reactor flying open cycle at Mach 3, spewing fission fragments directly into the atmosphere behind it. They built it. They tested it in the Nevada desert, and then they looked at what they had created and they realized a terrifying truth. This weapon was a thermodynamic nightmare. It was a machine that threatened its owner as much as its enemy. In 1964, the United States shut the program down. They buried the reactor in the desert and swore never to speak of it again. We thought the monster was dead. We were wrong. The grave has been robbed. In the frozen wastelands of the Arctic, the Russian Federation has just resurrected the technology the Americans were too afraid to use. They call it the Burevestnik. NATO calls it Skyfall. It is a nuclear-powered cruise missile with unlimited range. It is the ghost of Project Pluto, brought back to life with modern materials and zero moral restraint. This is the story of the flying Crowbar. We will deconstruct the engineering of the most dangerous engine ever built. We will analyze the physics that killed 5 Russian scientists in 2019 trying to salvage it. And we will show you why the weapon that terrorized the 1960s has returned to haunt the 2020s. Welcome to the edge of the impossible. This is Apex Engineering. To understand why rational men would build a flying nuclear reactor, we must first understand the irrational fear of the 1950s. The Cold War was not a static standoff. It was a race of escalating terrors. And in 1957, the United States believed it was losing. The psychological landscape of the West was shattered by 2 events. First, the Soviet detonation of a thermonuclear device, the hydrogen bomb, in 1953. Second, and more terrifyingly, the launch of Sputnik 1 in October 1957. To the public, Sputnik was a satellite. To the Pentagon, it was a proof of concept. If a Soviet rocket could lift a radio transmitter into orbit, it could lift a nuclear warhead to Washington, D.C. This birthed the missile gap. Intelligence estimates suggested the Soviets were churning out ICBMs. The American deterrent relied on the Strategic Air Command's bombers, the B-47 and B-52. But these planes had to fly high to reach their targets, and high-altitude airspace was becoming a kill-box. The Soviet S-75 Divina surface-to-air missile could reach 60,000 feet. The bombers were vulnerable. The solution was to go low. Radar cannot see through the curvature of the Earth. A vehicle flying at 500 feet is invisible to early warning radar until it is almost overhead. But flying low presents a problem of physics. But physics was only half the problem. The other half was politics. By 1958, the Pentagon was not just fighting the Soviets, they were fighting a civil war over the budget. The U.S. Navy was developing a game changer, the Polaris, a solid-fuel missile launched from a submarine. It was stealthy, survivable, and it terrified the U.S. Air Force. If the Navy could deter the Soviets from under the sea, why did America need the Air Force's expensive bombers? Enter General Curtis LeMay, the architect of the firebombing of Tokyo, the father of the Strategic Air Command. LeMay needed a weapon that had the endurance of a nuclear submarine, but the speed of a bomber. He needed to prove that the sky was still the ultimate high ground. This is where the third pillar doctrine was born. The Air Force argued that ICBMs were too rigid. Once launched, they couldn't be recalled. They pitched the SLAM as the perfect middle ground, a recallable robot. But recall was a lie. You cannot lend a nuclear reactor that is spewing fission products and has no landing gear. Recalling the SLAM meant crashing a billion-dollar machine into the deepest part of the Pacific Ocean. The Atomic Energy Commission was skeptical. They looked at the radiation projections. They looked at the cost. But LeMay and the Air Force brass were relentless. They argued that radiation was a manageable byproduct. They effectively cornered the AEC. If you don't build this reactor, you are admitting the Navy has won. Under this immense pressure, the checkbook was opened. The Air Force had their project. Now they just needed a miracle. At 50,000 feet, the air is thin. Drag is low. At 500 feet, the air is thick. It is soup. Flying at Mach 3 at sea level requires pushing through a medium that is exponentially denser. A conventional chemical engine would consume its entire fuel load in minutes just fighting this drag. To achieve global range at low altitude, the engineers needed a fuel source with an energy density millions of times greater than chemical combustion. A single kilogram of uranium-235 contains approximately 80 million megajoules of energy. A kilogram of oil contains 40. Nuclear fission was the only energy source that could decouple range from fuel volume. Thus, the order came down. Build a nuclear reactor that can fly at Mach 3. They called it Project Pluto. The engineering challenge of Project Pluto was not just difficult, it was hateful. The team led by the brilliant physicist Dr. Ted Merkel had to marry two technologies that hate each other, a nuclear reactor and a ramjet engine. A ramjet is the simplest type of jet engine. No compressor fans, no turbines. It relies on the sheer speed of the aircraft to ram air into the intake. In a nuclear ramjet, you replace the combustion chamber with a reactor core. The air enters at supersonic speed, passes directly through the white-hot reactor, picks up heat, and expands out the nozzle. To generate enough thrust to push a missile through the thick air of sea level at Mach 3, the reactor had to heat the air to 2,500 degrees Fahrenheit, or 1,370 degrees Celsius. And it had to do this while subjecting the core to 15 Gs of vibration and a pressure differential that would crush a submarine. Standard metals melt at these temperatures. Merkel's team realized the reactor couldn't be metal. It had to be ceramic. But who in America knew how to mass-produce high-grade, heat-resistant industrial ceramics to nuclear tolerances? The answer was sitting in Golden, Colorado, Coors Porcelain Company. Most people know Coors for the beer, but during Prohibition, to survive, Adolph Coors converted his bottling plant into a pottery works. They used the local clay to make scientific porcelain. By the 1950s, they were the world leaders in industrial ceramics. Project Pluto needed a mixture of uranium dioxide, the fuel, and beryllium oxide, the structure. Beryllium oxide is a paradox. It conducts heat like a metal, but resists heat like a ceramic. But beryllium is also toxic. The dust causes berylliosis, a fatal lung disease. Coors had to build a specialized sealed facility within their plant. The engineers at Coors developed an extrusion process to create the fuel elements. These weren't rods. They were hexagonal tubes, like hollow pencils. Why hexagonal? Because hexagons stack perfectly. They create a honeycomb. Coors manufactured 500,000 of these fuel elements. If a single tube was warped, it could block the airflow, creating a hotspot that would melt the core in milliseconds. The ceramics were solved, but the moving parts were not. The control rods had to be moved by pneumatic motors sitting right next to the superheated core. Radiation degraded standard lubricants. Heat flaked off standard coatings. They saw an advertisement for a high-temperature exhaust manifold paint used by drag racers, Sparex VHT. They bought a few cans, sprayed it on the actuators, and tested it. It worked. The multi-million-dollar nuclear missile was held together by spray paint from an auto shop. You cannot test a nuclear ramjet in a wind tunnel. The exhaust is highly radioactive. You need a place that is already desolate. You need Nevada. In Area 401, known as Jackass Flats, the government authorized the construction of the most dangerous railroad in history. The facility was designed around one central, terrifying fact. Once the engine was turned on, no human could ever get near it again. The center line was the test bunker. The walls facing the test stand were 6 feet thick. The viewing windows were made of leaded glass, layered with oil to stop neutron radiation. The glass was so dense it was yellow, casting a sickly light over the technicians inside. 2 miles away sat the disassembly building, or the hot shop. Since no one could touch the engine after a test, everything had to be done by robots. The hot shop was equipped with the largest remote manipulators ever built. Massive mechanical claws operated by technicians safely behind the concrete shielding. They were so precise they could thread a needle, yet strong enough to rip the steel casing off the reactor. To test the reactor on the ground, they had to simulate the airflow of a missile flying at Mach 3. This required a ton of air per second at high pressure. But the air also had to be hot. At Mach 3, air friction heats the intake to 1,000 degrees. Cold air would shatter the ceramic core due to thermal shock. The solution? A massive heater filled with 14 million steel balls. It took 2 weeks of continuous firing by oil burners just to bring those steel balls to temperature. 2 weeks of preparation for a test that would last 5 minutes. When the test began, the compressed air was blasted through this bed of hot steel, instantly heating up before smashing into the reactor. During the initial spin-up tests of the Tory II-A prototype, the engineers discovered a terrifying phenomenon: vibration. The air rushing through the hexagonal tubes at Mach 3 created a harmonic resonance. The ceramic tubes began to chatter. In one early low-power test, sensors detected a spike in exhaust radioactivity, a puff of dust.
The airflow was stripping the outer layer of the fuel elements. If this happened at full power, the reactor wouldn't just act as an engine, it would act as a dirty bomb, dusting the entire test site with pulverized uranium. By May 1964, the problems were solved. It was time for the Tory II-C, the flight-weight prototype. They opened the valves, the reactor went critical. For 5 minutes, the engine screamed at full power. It produced 513 megawatts of thermal energy. It generated over 35,000 pounds of thrust. The ground shook for miles. It worked perfectly. The ceramics held. The hot rod paint held. The flying crowbar was real.
The engine was ready. Now they needed the missile. The vehicle was the SLAM, the supersonic low-altitude missile. But the SLAM had a fatal flaw inherent to all ramjets. It cannot start from a standstill. A ramjet creates zero thrust at zero airspeed. If you turned on the reactor on the runway, it would simply melt through the tarmac. To fly, the SLAM had to be violently thrown into the sky. It would be strapped to a cluster of massive solid-fuel rockets, chemical boosters, that would drag the heavy reactor up to Mach 3. Only then, at supersonic speed, would the boosters fall away, the reactor vents open, and the nuclear heart begin to beat. The SLAM wasn't just a brute. It had to be smart. It utilized TERCOM, terrain contour matching. A radar altimeter scanned the ground, and a computer compared the valleys to a map stored in its memory. It was the invention of the digital map before the digital age. But there was a problem. The maps didn't exist yet. Satellites were in their infancy. The SLAM was built to fly through valleys deep inside the Soviet Union that the US had never even photographed. They built a machine to navigate a world they couldn't yet see. The SLAM was a triple threat weapon. First, the bomb. It carried hydrogen bombs in dorsal hatches, ejecting them upward to rain down on silos and cities as the missiles sped away. Second, the noise. A vehicle flying at Mach 3 at treetop level drags a shockwave of physical violence. A continuous sonic boom at 160 decibels is a hammer. It doesn't just break windows, it ruptures lungs, it bursts eardrums. It was a weapon of psychological torture, announcing its arrival with a sound that physically assaulted anyone on the ground. Third, the bonus. The Tory reactor was an open-cycle engine. It spewed radioactive isotopes directly into the slipstream. The strategists called it a bonus. Even after it dropped all its bombs, the SLAM could be programmed to keep flying. It could retrace its path, flying back and forth over the ruins of the enemy nation. While the exhaust was dispersed, the psychological terror of a radioactive robot circling overhead was absolute.
The Tory II-C test was a triumph, but on July 1, 1964, Project Pluto was canceled. Why? First, the ICBM. The Minuteman missile was entering service. It was fast, unstoppable, and chemically clean. And despite the Air Force's protests, the Navy's Polaris worked. The budget war was over. The Air Force lost. Second, where do you test it? You can run a reactor on a train car in Nevada, but you can't fly a spewing nuclear smokestack over the United States. If it crashed, you lose a state. But the ultimate reason was moral. The Pentagon realized that the SLAM was provocative. A low-flying, stealthy nuclear missile looks like a first-strike weapon. It encourages the enemy to launch on warning. The SLAM was a weapon that threatened its owner as much as its target. It was a sword without a handle. Project Pluto was buried. We thought the idea of a nuclear cruise missile had died with the Cold War. We were wrong. In March 2018, Vladimir Putin unveiled the 9M730 Burevestnik, NATO reporting name SSC-X9 Skyfall. It is a nuclear-powered cruise missile with unlimited range. Why resurrect a bad idea from 1964? Because of missile defense. The Burevestnik flies low, avoiding the high-altitude interceptors designed to kill ICBMs. But physics hasn't changed. On August 8, 2019, off the coast of Nyonoksa, a recovery operation went wrong. A reactor exploded during a salvage lift. 5 scientists were killed. But why did they die? A cold reactor sitting on the seabed doesn't just explode. The answer lies in the isotopes found in the atmosphere. Sensors in Severodvinsk detected strontium-91, barium-139, and barium-140. These are the smoking guns of nuclear physics. They are short-lived fission products. They decay away in minutes or hours. If this reactor had been sitting cold on the ocean floor for months, these isotopes would have vanished long ago. Their presence reveals the horror. The reactor was critical. It was running. Whether caused by seawater flooding the unshielded core and acting as a moderator, or a deliberate attempt to jump-start the engine during recovery, the physics are undeniable. The core went supercritical. The water inside flashed to steam in a fraction of a second. It was a steam explosion inside a nuclear furnace. The doctors who treated the survivors were not warned. They were exposed to cesium-137. It was a small-scale Chernobyl caused by the exact same engineering hubris that birthed Project Pluto. The Nyonoksa explosion proves that the flying crowbar is active. Unlike the Americans in 1964, the Russians have decided that the risk is worth it. They have solved the testing dilemma by simply accepting the pollution of their own Arctic waters. Project Pluto remains a singular monument to the atomic optimism of the Cold War. The engineers at Lawrence Livermore achieved the impossible. Their legacy lives on in the guidance of the Tomahawk missile and the industrial ceramics used today. But the shadow of the slam is long. It teaches us that just because we can build something doesn't mean we should. The slam was the ultimate doomsday device, a machine that worked perfectly, yet was too terrible to ever be used. There is a final bitter irony. Right now, in the Nevada desert, the U.S. government is actively demolishing Building 2201. They are tearing the concrete hot shop down to the dirt, erasing the last physical evidence that this monster ever existed. The Americans are destroying the grave at the exact moment the Russians are robbing it. Somewhere in the frozen north, the engines are roaring again. The crowbar is being forged anew, and this time there is no one left to cancel it.